Hello students, welcome to physics class. Today we discuss the motional EMF or induced EMF by change of area of the coil linked with the magnetic field. In the last session we learned that whenever the magnetic flux linked with a coil change, an induced EMF and hence an induced current produced in it. Now see the situation. We have a conductor of length L. PS is a conductor, metallic conductor of length L, which is free to move on a U-shaped metallic frame. Say the resistance of this metallic frame is very negligible and our conductor PS having a length L is free to move on this metallic ring. So all these arrangements are there in a uniform magnetic field of strength B, which is perpendicular to this plane of this board. We have a uniform magnetic field which is perpendicular to this plane. The strength of this magnetic field is B. And this metallic rail and our conductor PS is placed in this magnetic field. This conductor PS is free to move through this rail. And suppose we are moving this conductor PS with a velocity V in this direction. Say this PS is moving through this magnetic field on this rail with a velocity V in this directions. So whenever this PS is moving, we can say the area of this coil is changing. The area of this coil is decreasing. So we can say the flux associated with this coil is changing. So what happened? So an induced EMF will be induced in this coil. Let us see what is the magnitude of induced EMF and induced current. So we can call that induced EMF as motional EMF because it is the EMF produced across the end of this conductor once this conductor is moving through a uniform magnetic field. That is a motional EMF. So, suppose a length x of the loop inside the field. Here, the length of the loop which is inside the field is x. Inside the magnetic field is x at any instant t. So, what is the area of this loop at right? At this moment, the area of the loop is equal to L into x. Here, this side having a length L and this side having a length x at that instant t. So, L into x is the area which is inside this loop. So, we can say the magnetic flux associated with that loop at that instant is equal to phi is equal to B into A, where A is the area of this loop at that instant. So, B into A, B into L into x. Length into L into x, length into breadth, that is the area, L into x. So instantaneous flux is equal to phi is equal to BL into x. But that area is changing. Once the road is moving towards left side, area is continuously decreasing. So according to Faraday's law, once the area changes, we know that flux is also changing. So according to Faraday's law, an induced EMF is produced in it. So we can calculate the induced EMF E is equal to minus d phi by dt. According to Faraday's law of electromagnetic induction, E is equal to minus d phi by dt. That is minus d by dt of the phi. Phi is equal to B L into x. At that instant, the flux is equal to B L into x. So E is equal to minus into B into L is a constant. So we keeping it out, BL into dx by dt. dx by dt. You know, x is varying. Once the PS is moving towards left, the x is decreasing. So we can say the dx by dt minus dx by dt is actually the rate of change of the value of x. The time rate of change of the value of x. Once the x is decreasing, so minus dx by dt we can call as the velocity. We can say that the velocity is increasing in the direction of decreasing value of x. That's the minus value. shows. So minus dx by dt is equal to velocity. So we're writing that instead of minus dx by dt, we're writing velocity v. So E is equal to BVL. E is equal to BVL. That is the induced EMF developed between the end of the conductor PS. An induced EMF is developed between the end of this conductor, that's equal to BVL. What is E? E is the induced EMF between the end of this conductor. B is the strength of magnetic field. L is the length of this conductor and V is the velocity. So the factors affecting the induced EMF is the strength of magnetic field, length of the rod and the velocity at which it is moving. So an induced EMF is produced because of the motion of this conductor through a uniform magnetic field. So we calling this EMF as motional EMF. So once an EMF is developed between the end of this rod, a current is also flowing through this rod. So we can write the current is equal to the EMF by the resistance of this conductor. We can write the expression of the current later. So now you see what is the direction of current. So in order to predict this direction of induced current in this conductor, we can use this Fleming's right hand rule. We are already familiar with the Fleming's left hand rule. Now let us see what is the Fleming's right hand rule to predict the direction of induced current in the situations. So according to Fleming's right hand rule, if we stretch the thumb and the first two fingers of our right hand in mutually perpendicular direction, and if the forefinger point in the direction of B, thumb in the direction of motion of the conductor, then the central finger point in the direction of induced current. So let us apply the Fleming's right hand rule in the situations. First forefinger in the direction of magnetic field. Here the magnetic field is perpendicular to this plane of board and inboard. So the forefinger is in the direction of magnetic field. And now the thumb in the direction of motion of this conductor. In this situation, the conductor is moving towards left. So the thumb is in the direction of motion of the conductor. Now the thumb is in the direction of motion and forefinger in the direction of magnetic field. Now this middle finger direct in the direction of current. Now you can see that the middle finger is in downward direction. That is from P to S. In this situation, it is in the downward direction. That is from P to S. So that's the direction of current. So this current in P, Q or P, S is in this directions. So we can say in this frame, the current is flowing in this direction from P to S, S to R, R to Q and Q to P in clockwise direction. A current is flowing through this rectangular frame. Now let us find the magnitude of current through this conductor. We already seen what is the direction of current by Fleming's right hand rule. Now let us see what is the magnitude of current. The current in this loop is equal to I is equal to E by R. So current in this loop I is equal to E by R. Suppose R is the resistance of this conductor PS. And I already told that this rail having a negligible resistance. For our convenience, we are taking this R is the resistance of this conductor of length L, that is PS. And this rail having a very negligible resistance. So we can approximately write the current through this loop I is equal to E by R. What is R? R is the resistance of this conductor, and suppose this loop having a very negligible resistance. So I through this conductor can write as I equal to E by R. What is E? BVL divided by R. So that's the current through this conductor or current through this loop. So now we can consider this conductor PS is a current carrying conductor which is passing or which is moving through a uniform magnetic field. We already know that when a current passing conductor is moving through a magnetic field, it experiences a force. So that force is equal to strength of magnetic field into current into length into angle between the current and the magnetic field, BIL sine theta. Here, this is the length of the conductor, this is the direction of current. So, this is the direction of current. So, the angle between the magnetic field and direction of current is 90 degree. So, we can write as BIL into sine 90. That is the magnitude of force acting on this conductor. B is the strength of magnetic field, I is the current passing through this conductor, and L is the length of this conductor. And angle between the magnetic field and the current is 90. So, BIL sine 90. And so substitute for the current is equal to BVL by R. So that's equal to B into current, BVL by R into L. Sine 90 is 1. So we can rearrange this equation. The F is equal to B into B square, L square, V divided by R. So that's the force acting on this PS. B square, L square, V divided by R. Now what is the direction of that force? To find this direction of that force, we have to use Fleming's left hand rule. So remember, once you are applying Fleming's left hand rule, first forefinger in this direction of magnetic field, then middle finger in the direction of current. So in this situation, current is in downward direction and magnetic field is perpendicular to this plane, and so the thumb in right side, towards right side. So this is the direction of force. Just opposite direction of motion of the conductor, we have a force due to magnetic field towards right. But this coil or this conductor is moving towards left side. So in order to move this conductor towards left side, we have to provide a force continuously. We want to apply a force towards left side. Then only we can move this conductor towards left side. In order to avoid this opposing force, to overcome this opposing force, we have to apply a constant force of magnitude B square L square V divided by R towards the left side. Then only we can maintain the motion of this conductor. Now, once if you are continuously applying a force, a constant force to maintain this motion, we can calculate what is the power delivered by the external force. An external force should apply to move this conductor to oppose this the magnetic force. So what is the power delivered by the external force? So power delivered by the external force can be write as P is equal to F dot V. Power is equal to F dot V. So here the power is equal to F into V. So we can write as the power is equal to F is equal to B square L square V divided by R into V. So B square L square V square divided by R. So angle between this force and velocity is 0 because the object is moving, or PQ is moving in this direction towards left side. We are applying the external force in the same direction. So angle between F and V is 0. Applied force towards left side. The velocity is also in left side. So F dot V, we can simply write as F into V. F into V. Angle between them is 0. So F into V is equal to B square L square V square by R. That is the power delivered by the external force to maintain this motions. By the same time, you can see that some heat energy is produced in these coils. Once this process continue, some heat energy is developed in the coil because of the Joule's heating. So what is the power dissipated as Joule's loss? The power dissipated as Joule's loss. We know that power dissipated as Joule's law is equal to I square into R. I square into R. Power is equal to I square into R. What is I? B L V divided by R. I square B V L divided by R whole square into R. Again we are getting B square L square V square by R, which is similar to the equation the power delivered by the external force. So what does it means? The Pj, that is power delivered by Joule's laws, is equal to power delivered by the external force. So we can say once the process continues, first the mechanical energy. In order to move this PS, we want to apply some external force. So we are doing some mechanical work or mechanical energy is there. So mechanical energy is first converted into electrical energy. We know that an EMF and a current is produced in this coil. So first it's converted into electrical energy. Then electrical energy is converted into heat energy. So that much energy conversion is taking place here. Mechanical energy is converted into electrical energy. Electrical energy is converted into heat energy. And you see that the mechanical energy is equal to the heat energy produced. So it is the situation is consistent with the law of conservation of energy. The situation is consistent with the law of conservation of energy. That's all today. Thank you.